Good day, viewers. You are welcome to our today's video. So we are going to be continuing from where we stopped. We said we in our previous video we derived an equation for internal energy. Here we are going to be deriving an equation for enthalpy. We are going to be deriving an equation for enthalpy. So let's get straight into it. So enthalpy H, we said, is a function of temperature and pressure. So from our previous videos, we have already stated, we have already talked about the fundamentals of partial differentiation. So if we have enthalpy H to be equal to a function of temperature and pressure, where H here is the dependent variable, having T and P as the independent variable, we can say that the H is equal to the partial derivative of H all over the partial derivative of T, keeping P here constant, the T plus the H all over the partial derivative of P, keeping T constant, the P. So from our basic law of fundamentals of partial differentiation, we can derive this. It has been derived in our previous video, so you can refer back to our previous video for more understanding. So next, what we are going to be doing from our basic understanding of thermodynamics, we know that the change, that is the partial derivative of enthalpy, is equals to Cp, which is constant pressure, multiplied by the partial derivative of temperature, which is the T. So next, they are going to be, and this is for an isobaric process. So what we are going to be doing next, we are going to be making constant pressure, which is Cp, the subject of this relation. So in doing that, we are going to be dividing both sides by the partial derivative of T. To do that, Cp will be equal to the H, that is the partial derivative of H over the partial derivative of T, keeping P constant. So this is what we have. So we are going to substitute Cp in this equation for this, because the partial derivative of H over the partial derivative of T, keeping P constant, is equal to Cp, and we have it here. So we are going to be substituting Cp in this equation. So if we do that, the H will be equal to Cp dt plus the partial derivative of H dP. So this is what we have. So entropy, we are going to be relating this equation with entropy. So entropy now, in order to derive the enthalpy equation that will be used for thermodynamic analysis, we are going to be involving entropy. So if we involve entropy, we can say that entropy S is equal to a function of temperature and pressure. That is when we are dealing with enthalpy. So if we have this here, from our basic law, like I said before, of partial differentiation, we can say that the S is equal to the partial derivative of S over the partial derivative of T, in P constant, the T, plus the partial derivative of S over the partial derivative of P, keeping T constant, the P. So this is what we have. Now, from our basic law of thermodynamics, that is our first law of thermodynamics, we know that from our first law of thermodynamics, we know that the Q, okay, not from the first law, we know that enthalpy, because we are trying to derive an equation for enthalpy, which will be used for thermodynamic analysis. So we know that enthalpy H is equals to U plus PV. So this implies that the H, if we differentiate, will be equals to the U plus P dV plus V dP. That is using Using product rule to differentiate this, we are going to have P dV plus V dP. So if we do this, this is what we are going to have. So next, we know that the Q from our first law of thermodynamics is equals to the U plus P dV. And we also know from our second law of thermodynamics that the S, the S rather, is equals to the Q. So if we equate these both equations, we are going to have CdS is equals to du plus P dV. So now we are going to be substituting CdS. CdS is equals to du plus P dV. So we can substitute du plus P dV is equals to CdS in this equation. So if we do that, we have the H is equal to CdS. The H will be equal to CdS plus VdP. We have H is equal to CdS plus VdP. Now we are going to be substituting, we can call this equation 1. Let's call this equation 2. We are going to be substituting the value of the S, which is this, for the S in this equation. So if we do that, we are going to have the S, we are going to have the H rather to be equal to T into the bracket of the partial derivative of S over the partial derivative of T, keeping P constant, dt plus the bracket of the partial derivative of S over the partial derivative of P, keeping T constant, dP, close bracket, plus VdP. So this is what we have. So we are going to be opening this bracket with T. So if we do that, we have the H will be equal to T into the bracket of the partial derivative of S over the partial derivative of T, keeping P constant, dt plus T into the bracket of the partial derivative of S over the partial derivative of P, keeping T constant, dP plus V dP. So this is what we have. So if we look at this equation, you will discover that the P is common. So if we factor out the P here, we are going to be having the H to be equal to T, the partial derivative of S over the partial derivative of T, keeping P constant, dt, plus the bracket of T into the partial derivative of S over the partial derivative of P, keeping T constant, plus V, close bracket, dP. So this is what we have. So if you look at these both equations, we have the H in equation 1 to be this, and we have the H here to be this. So what we do next is that we are going to be comparing both equations. So I will rewrite the equation. We have equation 1 as the H to be equal to the P, the T, plus the H all over the partial derivative of P, keeping T constant, dP. This is our equation 1. So we can say, let this be equation 3. And if this is equation 3, we can write this as the H is equals to T into the bracket of the partial derivative of S over the partial derivative of T, keeping P constant, dt plus the bracket of T into partial derivative of S over partial derivative of P, keeping T constant, plus V dP. So this is what we have. So if you compare both equations, you can see that the coefficient of the T is T into the partial derivative of S over the partial derivative of T, keeping P constant, and the coefficient of the T here is Cp. So we can equate both equations. We are going to have Cp to be equal to T into the bracket of the partial derivative of s over the partial derivative of t, keeping p constant. To do the same thing for here, we are going to have the partial derivative of h all over the partial derivative of p, keeping t constant, to be equal to t into the bracket of the partial derivative of s over the partial derivative of p, keeping t constant, plus v. So this is what we have. So next, we are going to be relating this equation with the Maxwell equation. We know that the s all over the p, keeping t constant, equals to minus the v all over the t, keeping p constant. From our Maxwell equation from our previous video, we know that the partial derivative of s over the partial derivative of p, keeping t constant, is equals to minus the bracket of the partial derivative of v over the partial derivative of t, keeping p constant. So next, we are going to be comparing this equation with this one. So here we have the partial derivative of s over the partial derivative of p, keeping t constant, and here we have the partial derivative of s over the partial derivative of p, keeping t constant. So we are going to be substituting the value of this into this equation. So if we do that, we are going to have the bracket of the partial derivative of h over the partial derivative of p, keeping t constant, will be equals to t. So for this value here, we are going to be substituting this. So we have the bracket of minus the partial derivative of v all over the partial derivative of t in p constant plus v. So we can further say that the partial derivative of h over the partial derivative of p in t constant is equals to minus t into the bracket of the partial derivative of v over the partial derivative of t, keeping p constant, plus v. So what we are going to be doing next is we are going to be substituting this into our equation 1. So equation 1 says the h is equals to Cp dt plus the partial derivative of h over the partial derivative of p, keeping t constant, dp. So from equation 1, substitute this value. From equation 1, the h is equal to Cp dt plus the partial derivative of h over the partial derivative of p, keeping t constant, dp. This is equation 1. So we are going to be substituting this value for this in equation 1. So if we do that, the h will be equal to Cp dt plus the bracket of minus t into the partial derivative of v over the partial derivative of t, keeping p constant, plus v. So this is the h. So it implies that the h will be equal to Cp dt minus t, the bracket of the v, dt of p, plus v. But don't forget, we have the p here, so we are going to be having this multiplying the p. So this is what we are going to have. The above equation is used to calculate enthalpy. Write this by saying the h is equal to Cp dt into the bracket of v minus t into the partial derivative of v over the partial derivative of t, keeping p constant, dp. So this equation is the equation of involving it's a thermodynamic equation involving enthalpy, which can be used for thermodynamic analysis. So the above equation is a thermodynamic equation involving enthalpy for thermodynamic analysis. Thank you.